In this video, let's solve Leetcode 42, which is trapping rainwater. This is a very interesting question, and we will be discussing two ways in which you can solve this question. First, let's read the question and try to really understand what is asked of us. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. Okay, so this is the question, and we have a few examples over here. So this is one example. If this is the array which is given to us, then you can see that it can be visualized in this manner, and because of this, if it is raining, the amount of water that would be trapped is given as 6, which is what you can see over here. 1, then you have 1, 2, 3, 4, and then you have 1. So 4 plus 1 plus 1 is equal to 6, and that's the answer. Okay. Now let's try to take a deeper look at the example given over here. So this is the array, and let's see how we can visualize it in this manner. So over here, I have the array which is given to us. So notice that for every height, we would be drawing a bar in this manner. Like over here, the height is 0. So I can draw a bar over here, and then I have 1 over here. So I'm drawing 1 over here, which is at 1 unit. Again, I have 0, then I have 2. So this would be 2, right? So this is 1, this is 2. So that's why I would be drawing the bar with the height 2, and it goes on in this manner. So in this way, I would be drawing all these bars based on the height array which is given. And in the question, it was mentioned that the width is the same for every bar. So that's why the width is uniform. It's always 1 unit. Okay, that's on the x-axis. Now, once you have that, notice that you can just connect it to the bottom in this manner. Like you have a height over here, we are connecting it down. Similarly, you have this height, we can just connect it down, but we would be only connecting up to here because there is a height over here. This is equal to 1 over here, right? So that's why we would just connect it in this manner. And then again, this can be connected down. And in this manner, we are getting this structure over here from the input array. Okay. Now imagine that you're pouring water on top of it, which is given in the question that it's raining, right? So let's say it's raining. Now in this case, over here, water will not be stored because there is nothing, there is no wall to prevent water from draining out on the left, and on the right also over here, water would just be spilling over here. But notice that water which comes over here will only spill after 1 unit of water is contained over here, because there is a wall over here and there is a wall over here. Only anything above 1 unit would spill over. So over here in this particular position, we are able to store 1 unit of water. Similarly, notice that the structure is looking like this over here. So that's why we are able to store 1 unit of water over here, and then we are able to store these 3 units of water over here, and anything in addition to that would be spilling over, because over here there is an opening after that, right? So water would be filled up to here, and if you pour more water in, it would just spill over. So that's the idea behind this question. So we are given this array over here, and then the meaning of this array is what we have seen over here visually, and based on that, based on the given array, we'll have to compute the amount of water that we can store at each index. Like for example, at index 2, we can store 1 unit. At index 4, I can store 1 unit. At index 5, I can store these 2 units. At index 6, I can store 1 unit of water. And at index 9, I can store 1 unit of water. Now, if I add up all of these, I get the answer. So we have got a good idea of what is asked of us. Now, before we proceed and try to solve this question, let's make a few interesting observations. First of all, how would we compute the amount of water that I can store at a particular index? For that, let's take a few examples over here. For example, at index 2, visually we can see that I'm able to store 1 unit of water. But how does that actually translate, or how do we actually convert this into a logic which we can code out? Okay. So again, notice what's happening over here is that this one can be obtained by taking the minimum between these two walls. So there is a wall over here of height 1. There is a wall over here of height 2. Okay. Now if I take the minimum between these two, I get 1, which is the amount of water that I can store over here. So this is our first observation. We'll have to find the minimum between the two sides at every index. So this is the first observation. Okay. Now again, technically it's not correct that we are taking the minimum between 1 and 2. And let's take a look at that as the next observation. So far we have understood that we have to identify the minimum between the walls at the left side and the right side to get an idea about how much water can be stored. But what about index 5? Okay, so notice at index 5, visually you can see that we are able to store these 2 units of water, but their immediate boundaries for the position index 5 has just height 1 and height 1 over here and here. Okay, so the minimum between these two would be 1 itself, and again we can clearly see that I'm able to store 2 units of water. So what we would need to do is we'll have to identify for every position the maximum to the left and the right. So for example, at index 5, the maximum to the left is 2. You can see that that's over here. So the maximum is 2 to the left, and the maximum to the right is 3, which is this over here. Now we would have to take the minimum between these two, which in this case is the minimum between 3 and 2, which is equal to 2. And you can see that, yes, that makes sense. We are able to store, in fact, 2 units of water. So this is what we have understood so far. To identify the amount of water that I can store at every index, I will have to identify the minimum between the left max and the right max at every index or every position. Okay. Now the second thing that you can notice is from this, you would have to subtract the height at that particular index. Now why is that so? Let's again take an example to understand this. Like for example, let's take index 4. Okay. So the maximum to the left for this particular position, we can see that is 2, which is over here, and the maximum to the right of this position is equal to 3, which is over here. Okay. Now the minimum between 2 and 3 is equal to 2. So we are getting 2 over here as part of step 1 for this particular position. Okay. But visually you can see that you're able to store only 1 unit of water and not 2 units. Now why is that so? Because this over here also has a height. Like if this was 0, if it was over here, then you would be able to store 2 units of water over here, which is the minimum between 2 and 3. Okay. But there is a height over here which reduces the amount of water that you can store at this position. And that's why you'll have to take the minimum between left max and right max and subtract the height at that particular position from the minimum over here. So in this case, that would be the minimum between 2 and 3, which is 2. And from this 2, you'll have to subtract this height, which is equal to 1. And you will be left with 1, which is the amount of water that you are able to store at this particular index. Okay. So we have made an interesting observation. Like in fact, we have made 2 observations. So the first thing is that we'll have to identify the minimum between left max and right max at every index. And the second observation that we made is that from this, we'll have to subtract the height at that particular index. So this would give us the amount of water that we can store at that particular index. Now let's discuss one more interesting observation, and then we can proceed and solve the question. Okay. So what we can see over here is, like, let's take an example. At index 3, the maximum to its left is equal to 1, which is over here, and the maximum to its right is 3. Okay. Now the minimum between 1 and 3 would be 1. So we get 1 over here, and the height at index 3 is equal to 2. So we would be subtracting 2 from 1, and this gives us minus 1. Okay. Now minus 1 units of water does not make sense. So you can handle it in 2 ways. One way would be, if you're getting a negative value, you can just take it as 0 Okay, and again you can see that that's the case visually as well. You're not able to store any water over here. But you can also handle this in another manner, which is when you compute left max, you have to take the maximum of all left values. Let me write this one more time. So when you compute left max, you will have to take it as the maximum of all left values, the height at that particular index. Again, let me explain this. So far, the way that we have discussed left max is, like for example at position 3, we would only consider position 0, 1 and 2. All of these positions are to the left of position 3. Okay, and for right max, we were considering all of these positions which are to the right of this particular position. But instead of doing it this way, if you take left max as the maximum between all of the values to the left and the value at this particular index. So you're considering all of these positions for left max, and you're considering all of these, that is all of the values to the right and this value for right max. So these are the values that you will consider for right max, and all of these are the values that you will consider for left max. So if you do it in this manner, you're ensuring that left max will never be less than the height at that particular index. Similarly, right max will never be less than the height at this particular position that we are talking about. And in this way, when you do minimum between left max and right max and you subtract height at index I from it, you will never get a negative value. Now logically also this makes sense, because we want the minimum between left max and right max only when that minimum is greater than the height at that particular position itself. If the minimum between left max and right max tends to be less than the height at the index that we're talking about, then we would just want it to give us the current height, and in that way we do current height minus current height, which is equal to 0, and we are avoiding getting a negative value. Okay, so let me quickly summarize the observations that we have made so far. The first observation that we made is that to find the water that we can store at a particular index, all that we need to do is we need to find the minimum between left max and right max, and from this we'll have to subtract height at index I. Okay, now the second thing that we've discussed is how do we compute left max and right max, or what are the values that we consider when we try to find left max and right max. And we've discussed that, let's say we are trying to find left max and right max for index 4. So we would consider index 0, 1, 2, 3 and 4 for left max, and we would consider index 4 up to 11 for right max. Or in other words, for each of these, we are also considering the index that we are talking about, and in this way, we ensure that the minimum between these two will never be less than height at index I, and therefore this will never give us a negative value, and we can just find this and keep adding this to a variable, and finally we can just return that variable as the answer to the question. Okay, so we have thoroughly understood the question and we have made a few interesting observations. Let's now proceed and solve this question. We'll be discussing two approaches. The first approach is using two auxiliary arrays, and the second approach will be without using any auxiliary arrays, and that would be just by using two pointers. Okay, so we'll discuss these two methods to solve this question. Now, the method using the auxiliary arrays is pretty straightforward. We have this array which is given to us. Now, we know that from our discussion so far that for each index, we would need to know the left max and right max. And if we know that, we can find the water by computing the minimum between these two and then subtracting height at index I from it. So that's what we have discussed so far. Now, using two auxiliary arrays, we are just implementing this straightforward, and we are storing, like instead of computing left max and right max for every index again and again, we are just going ahead and storing it as we compute it. So this is a dynamic programming approach. Okay, now again it's pretty straightforward. So let's quickly walk through what we would do in this approach using this example. Okay, so again, we have these values over here. Now, first let's fill the left max array. So this would be an array. So initially, left max at index 0 is 0. Okay, and again, we would consider anything to the left of this particular position, which in fact is nothing, and this position. So the maximum value is 0. Now, left max at this position would be the maximum between the value that we have at this particular position and the left max value that we so far have, which is 0. So the maximum between these two is 1. And again, the left max at this particular position would be the maximum between what we have so far in left max, which is 1, and the value at this particular index, or the height at this particular index, which is 0. So the maximum between these two is 1. Similarly, over here, the left max for this particular position, again, it's just the maximum between all these values, right, which is equal to 2. And over here, the left max would be the maximum between all these values, which would be again 2. And over here, the left max would be the maximum between all these values. And again, I'm just showing that visually. We don't need to again iterate over all these values. We already have the maximum between all these values, which is 2. And then this is the new value. So we just need to know the maximum between these two values, which is again 2. And then the maximum between these two values is 2. The maximum between these two values is 3. The maximum between these two values is 3. And between these two it's 3. And again we have 3. And again we have 3. In this way, we are able to fill the max left array. Now let's see how we can fill the max right array. Again, we start over here. Okay. And the maximum right value for this position would be the maximum between any values to its right and this. Now we don't have anything over here, and this is the only value that we have. So the maximum right value for this position is 1. And then we move to the next value over here. And the max right value over here would be the maximum between this and this, which is equal to 2. Again, the next max right value would be the maximum value between all these values, which again is 2. And then we have the next max right value over here, which would be the maximum between all these values. And again, you don't need to iterate again and again. You just need to check the maximum between what you already have at max right and the new value which is coming in. So again, we have 2 and 2. The maximum between these two is 2. And then we have 3 and 2. The maximum between these two is 3. And over here also we would have 3 because that's the maximum between 1 and 3. Similarly, over here also we have 3, 3, 3, 3, 3, and 3. All right. So far we have filled the maximum left and maximum right auxiliary arrays. Now we just need to find the minimum between these two. So the minimum between these two, between 0 and 3 is 0, between 1 and 3 is 1, between 1 and 3 again is 1, between 2 and 3 is 2, and over here we have 2, we have 2, we have 2, we have 3, we have 2, we have 2, we have 2, and we have 1. So these are the minimum values. And we have discussed that you just need to find the minimum between left max and right max, and then from it you'll have to subtract height at index I. Okay, so let's go ahead and see how much water can be stored in each position. So we have the minimum over here, and from this let's subtract height at index I, which is what we have over here. So 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 2 minus 2 is 0, 2 minus 1 is 1, 2 minus 0 is 2, 2 minus 1 is 1, 3 minus 3 is 0, 2 minus 2 is 0, 2 minus 1 is 1, 2 minus 2 is 0, and 1 minus 1 is 0. So that gives us the answer. So again, we have 1 unit of water over here. We have 1 and 2 and 1, and then 1 unit of water over here. So the total is equal to 6 units of water, which is the answer. So this is the first approach which we can use to solve this question using two auxiliary arrays. Notice this is a dynamic programming approach because we are storing the left max and right max in two arrays, which helps us because we don't need to keep looping over the elements again and again to find left max and right max at each respective index. Let's now proceed and code the approach that we have discussed over here. Let's now get into the code and code the first approach that we have discussed, which is using two auxiliary arrays. Okay, so we have the list over here which is given to us, which is height. Now to start with, let's take care of an edge case. So if the length of the height array which is given to us is equal to 0, then we will just return 0 because we will not be able to store any water. Now we'll also have a variable, let's call it ans. Okay, so this will be the value that we will finally return, which will be the units of water that can be stored for the given height array. Okay, and we will also need two auxiliary arrays of the length equal to the length of the height array which is given to us. So first let me say size is equal to length of height. Okay, and then let's call the two auxiliary arrays left max and right max, and each of these is going to equal an array where we'll just fill every value with 0, and the length or the size of these two auxiliary arrays will be the size of the input array, which is height. Okay, so left max is this array and right max also is this array. Now we will have to go over the indices and fill the left max and right max for each corresponding index. Okay, so again let me just have a placeholder over here. So let's say fill left max array, and then I'll fill the right max array, and then we'll go ahead and compute the water that we can store. So this is the approach that we will be taking over here. Now before we go ahead and do these two parts, let's also mention over here that left max at index 0 is going to equal height at index 0. Okay, so because so far there's nothing to its left, so for that particular index the height at index 0 would be the left max. Now again remember, we have already discussed it in the previous sections that for a particular index the left max will be the largest value to the left of that index and including that index. Okay, the values to the left of that index and including the value at that index. So again the logic for that we have already discussed previously. So that's why over here I'll set left max at index 0 to be height at index 0, and similarly right max at the last index, which would be size minus 1, is going to equal height at size minus 1 because there's nothing else to its right. Okay, so there's just the value which is there at that particular index, and that's why we will set right max at this particular index to be height at size minus 1. Alright, now let's proceed and fill the left max array. So I can say for I in range 1 to size, because we already have the value for index 0, right? We have already set it over here. So that's why we can start at index 1 and we'll be going till the last index. And left max at every index is just going to be the maximum between what we have at that index, which would be height at index I, and the left max value at the previous index, which would be left max at I minus 1. Okay, so in this way we would be iterating over the array, the height array which is given to us, and we will be filling values accordingly to the left max array. Now let's also do the same thing and go ahead and fill the right max array. Again I'll say for I in range, and at this point we will be starting at the second last index, which would be size minus 2, because we have already filled the value at the last index. Okay, so we'll start at size minus 2 and then we'll keep decrementing by 1, and we want to go till index 0. So that's why we have minus 1 over here. And then I can say right max at index I is equal to the maximum between what is there at height at index I and the right max value at the next index, because we are going from the last index to the first index. So that's why the previous right max in this case would be right max at index I plus 1. Okay, so in this way we have filled our left max array and the right max array. Now we will just go over every index. So I can say for I in range, and I'll start at index 1, and we only need to go till the second last index, because as we have discussed previously, we will not be able to store any water in the first index, which is 0, and in the last index, which is index size -1. So that's why we don't need to go and check the water that can be stored in those two places, and we just need to check the remaining indices. So that's why we can have the range over here 1 comma size -1, and then at every index the water that we can store at that particular index would be the minimum between left max at index I and right max at index I, because that's the constraint, right? The minimum between these two will be the constraint, because any water above that would spill over, as we have discussed previously. And then once we get the minimum between these two, we'll also have to subtract height at index I from it. So this would be the water that we can store at index I, and then we can just say answer plus is equal to this, because as we get values for the units of water that can be stored in each index, we don't need to store that, we just need to finally be able to return this answer. So we'll keep adding that to our answer, and then finally we will be returning the answer. So this is the first approach that we have discussed with which we can solve this question. Now let's go ahead and run this code and see if it's passing all the test cases. Okay, so we have a typo over here, so let me just quickly correct that. It should be GHT. Okay, now again let me run this, and you can see that it's passing the test cases. Let me submit it, and yes, you can see it's accepted. It's passing all the test cases. So this is the first approach with which we can solve the trapping rainwater problem. Now let's proceed and take a look at the 2 pointers approach. Alright, so we have discussed the first approach and we have also coded it. Now let's discuss the 2 pointer approach which you can use to solve this question. Now in this case, you will only need O of 1 space complexity, because we will only iterate over the row one time. So the time complexity remains O of n, but the space complexity is just going to be O of 1, because we are not going to use auxiliary arrays, but we will just have a few variables like left, right, pointer, etc. Okay, so that's the advantage. For the previous approach, the time complexity was O of n, and the space complexity is also O of n, because we used 2 auxiliary arrays. But over here, using 2 pointers, we'll be able to do it in O of n time complexity and constant space complexity. So let's get started. Now in this approach, we are going to have 2 pointers, and let's call it left and right. And initially, left will point at the leftmost position and right will point at the rightmost position. Now we are also going to have 2 variables, left max and right max. So left max is going to be the tallest bar we have seen from the left. Similarly, right max will be the tallest bar that we have seen from the right till where the 2 pointers have reached from their respective ends. Okay, so we are going to keep track of this on the fly. Now again, this will become clear as we proceed and walk through with an example. Now let's proceed. So far we have discussed that we have a left pointer and a right pointer, and we have these 2 variables to keep track of left max and right max. Now before we proceed, one more quick observation. We have discussed that we will not be able to store any water in the 2 far end positions, because there is no wall to the left of this position and there is no wall to the right of this position. So any water would just spill out. Okay, so that's why we will not be able to store any water in these 2 far extreme positions. Now let's proceed and see how we can solve this question using 2 pointers and without any auxiliary arrays. And again, also notice at this point left max is equal to 0 because we have 0 over here, and right max is equal to 1 because we have 1 over here. So the left pointer has only visited this position so far, so that's why the value of left max at this point is 0, and the right pointer has only visited this position so far, because of which the value over here is equal to 1. Now here comes the big idea. At every step we will compare left max and right max, and whichever is smaller we will move the pointer accordingly. Like if left max is smaller, we will move the left pointer, and if right max is smaller, we will move the right pointer. Again, why is that so? Because remember, what we have discussed so far is we would be calculating the minimum between left max and right max at every index, and then we would be subtracting height at that particular index. This would give us the amount of water that we can store at a particular index. So notice we only need the minimum between left max and right max. Okay, so whichever is smaller is sufficient for us. We don't need to know both of them. So that's the intuition behind this approach. Now let's see this in action. So over here, notice left max is 0 and right max is equal to 1. Between these, 0 is less than 1 or left max is less than right max. Okay, now because left max is less than right max, we will move the left pointer, which is this pointer over here. Okay, so we will move the left pointer one step ahead. So again, it will move from index 0 to index 1. So I've moved the left pointer one step ahead and it's pointing over here. Now our aim is to calculate how much water I can store in this position. These two have already been computed, and as we keep moving the pointers, we will just try to compute the water that we can store at that particular position. Okay, so let's try to compute how much water I can store over here. And this is where the magic happens. We know that left max is less than right max. Okay, and therefore in our formula, like we had minimum between left max and right max minus height at index I. And over here, we know left max is less than right max. So we don't need to consider right max because left max is the smaller value. And that's why water that can be stored at this particular position will be left max minus height at left. And again, left is just the position. So instead of I have left. But over here, notice I am no longer calculating the minimum between these two because I know left max will be less than right max. Like I have a value for right max at this place, right? But again, typically we used to consider all of these values. But again, even if you consider all of these values, right max can only increase. It cannot decrease because we are trying to find the maximum. So at this point already, we know that left max is less than right max. So even if right max keeps increasing, left max would still be less than right max. And that's why we don't need to compute the minimum between these two. We already know that that's going to be left max. And hence we can say that water at index left is going to be left max minus height at left. And in this case, that's 1 minus 1, which is equal to 0. And again, remember one more point. We have already discussed this previously. Left max will be defined as the height of all the values to the left of a position, including itself. Like if you want to know left max at this place, we would consider all of these values, including this value. And again, we have discussed the reason for that. It will help us avoid negative values. Okay. So again, let me quickly recap. We found that left max was less than right max or 0 less than 1. Therefore, we decided to move the left pointer. So we moved this ahead and we compute the new left max, which at this point is 1, which is the maximum between what we had and the value over here. The maximum between these two is 1. So we compute the new left max and then we compute the water that we can store at this index as left max minus height at this particular place, which is 1. Okay, so left max is 1 and height at left is 1. So over here, the water that we can store is 1 minus 1, which is equal to 0. Again, the thing that boggles our mind sometimes is that we are not considering right max any longer. We are only considering left max because we know left max is less than right max, because that's why we moved the left pointer, because left max was less than right max. Okay. Now again, quick side note, you may think we are computing the left max again over here, right? So initially left max was less than right max, but could there not be a case because we are recomputing the left max that it could be greater than the right max? Now again, it's a valid question. It can be a possibility, like you could have, like say, let's say you have 10 over here. So when you compute the new left max, this will become 10 and that's greater than right max. So would that not be a problem? The answer to that is it would not be a problem, because remember, when we compute left max and when we compute right max, we are considering the height at this particular index in both the cases. So if this is a very large value, then we would just want the minimum between left max and right max to equal the height at this particular place, so that height minus height will give us 0. Okay, so we have discussed that. Again, at every index, we take the left max and right max, including the value at that particular index, so that we never get a negative value. So because of that, this is not a problem. We just want to know the minimum between left max and right max in this case without considering the value over here. And because we already know that from this comparison, we already know that in this case left max is less than right max. Therefore, to compute the water that can be stored at this particular index, we just have to do left max minus height at left. Okay, now just to make it one more time clearer, you could write this as, again, I'm just writing it in a way that it becomes easier for us to think about this. You could think of this as the maximum between left and current place. Okay, now if you think of the formula that we had minimum between left max, right max minus height at index I, and for each of these, left max was the maximum between left and current. Similarly, right max was the maximum between right and current value. So that's how we computed left max and right max. So basically, left max and right max can never be less than the current height, and therefore even updating the left max over here is not a problem. So quickly summarizing once more, we checked which is smaller, left max or right max. Over here we saw that left max was smaller, therefore we decided to move the left index. The second thing is we computed the new left max, and thirdly we were able to compute the water that can be stored at this particular position by doing left max minus height at left. We did not need right max. So in this way we are able to see that we can store 0 units of water over here. Now let's proceed. So at this point left max is 1, right max is 1. Okay, and because they are equal, you could move any of them, but let's say if they are equal, we decide to move the left pointer. Okay, so I'm going to move the left pointer ahead, so it comes over here, and I moved the left pointer, therefore I will update the left max. So again I got 0, so the left max stays 1 itself, it does not change, it's the maximum between all these values. And then because I moved the left pointer, I can compute the water at this particular place as left max minus height at left. Again notice we did not need right max. So in this way I get the water that can be stored at this particular place as left max, which is 1, minus height at this particular place, which is 0. So that's this 0 over here. 1 minus 0 is equal to 1, and therefore I can store 1 unit of water over here. And then we again proceed. Again you see that left max and right max are equal. So again you could write the logic in either way, but let's say we write it in a way that if they are equal, we will move the left pointer. So I'm moving this pointer ahead. Okay, so it's pointing over here, and again we update left max. So at this point I got a greater value, so left max has to be updated to 2, and I moved the left pointer. Therefore water at that left pointer is going to be left max minus height at left. So left max is 2 and height at left is 2, so 2 minus 2 is equal to 0. So that's why I can store 0 units of water over here. Again we proceed. Okay, so you have 2 and 1 over here. Now at this point notice that right max is less than left max. Okay, now if right max is less than left max, we'll have to move the right pointer. Okay, so let's go ahead and do that. So I move the right pointer, it comes over here, and I update the right max, because the right max will be the maximum of these values, and you can visually see that the value 2 is greater than 1. Okay, or I'm comparing the previous right max with the new value which is coming in, which is 2. So I update the right max value, and then, so again, what are the steps? One is that I was able to decide that move the right pointer because right max was less than left max. The second step is update the right max or compute the new right max. And then we can say water at index right, which is at this position, will be right max minus height at right. Again, we don't need left max over here because right max is less than left max and we need only the minimum between them. Okay, so right max over here is 2 and height at right is equal to 2. So 2 minus 2 is equal to 0, and that's why over here I can store only 0 units of water. Let's proceed. So at this point, left max is 2 and right max is equal to 2. They are equal. So again, we have decided to write the logic in a manner that if they are equal, we will move the left pointer. So I will move the left pointer ahead. Okay, so it's pointing over here at this moment, and I update the left max if required, but again I got just a value 1 which is less than the previous left max, so I don't need to update this, and I compute water at this particular place, which is water at left, is equal to left max minus height at left. And that's 2 minus 1, which is equal to 1. So that's how I get 1 over here. Again, let's proceed. Left max is 2, right max is 2, they are equal, therefore we will move the left pointer. The left pointer is pointing over here, and we don't need to update left max. We got 0, we had 2, 2 is greater than 0, we don't update this. And then we compute water at this place, which is water at left, is left max, which is this 2 over here, minus height at left, which is equal to 0. Okay, and 2 minus 0 is equal to 2, and that's why over here I can store 2 units of water. Again, we proceed. Left max is equal to right max, so I move the left pointer. Okay, it's pointing over here, and I get 1. I had 2 over here, so 2 is greater than 1. I don't need to update left max. And then I say water at left, which is water at this place, is left max, which is 2 minus height at left, which is 1. 2 minus 1 is 1. So that's how I get that I can store 1 unit of water over here. Okay, now let's proceed. Again, left max and right max are equal. Therefore, I move the left pointer, and the left pointer is pointing over here, and the value that I get is 3. Previously, left max was 2. 3 is greater than 2, so I have to update left max, and at this point, left max is equal to 3. Okay, and I moved the left pointer. Remember, I moved the left pointer. Therefore, I computed the new left max, and I say water at left, which is water at this new position to which I moved the left pointer, is equal to left max, which is 3 minus height at left, which is 3. This 3. Okay, so 3 minus 3 is equal to 0, and that's why the water that I can store at this position is equal to 0. Now we compare left max and right max, and we see that right max is less than left max, and therefore we have to move the right pointer. Okay, so I move the right pointer, it's pointing to this position, and I see whether I need to update the right max. Right max was 2, the new value is 1, so I don't need to update right max, and I compute water at right is equal to right max, which is 2 minus height at right, which is 1, this 1 over here. 2 minus 1 gives me 1, and that's how I get that I can store 1 unit of water in this position. Okay, again I compare left max and right max. Right max is less than left max, therefore I move the right pointer. I move the right pointer, it's pointing to this position. Okay, and I get the value 2. I already had 2 over here, so I don't need to update right max, and water at right, which is the water that can be stored at this position, is right max, which is 2 minus height at right, which is this 2 over here, and 2 minus 2 is equal to 0. So that's how I get that I can store 0 units of water over here. And again, in the loop, right, you would be writing a loop like while left less than right. Okay, so at this point, again we see that right max is less than left max. We would move the right pointer, but then it would become equal. Left and right would become equal, and we will come out of the while loop and notice that we did exactly one pass over the array which was given to us, and we would have found the water that can be stored for the array given to us. So this is how you can solve this question using the two pointer method. And the advantage is that the time complexity is still O of n because we are doing one pass, but the space complexity is O of 1 because we are not using auxiliary arrays like we did in the previous method that we have discussed in this video. Let's now proceed and code out the approach that we have discussed now. Let's now implement the two pointers approach for solving the trapping rainwater problem. Okay, so we've already discussed the method that we're going to use, and over here let's get into the code. So to start with, we're going to have two pointers, left and right. Okay, and left is going to point to index 0 and right is going to point to the last index, which is length of height minus 1. Okay, and we also need a variable to store the amount of water that we will be able to store based on the array which is given to us. So let's call that answer, and initially answer is going to equal 0, and ultimately we will be returning answer. Okay, now we also need two variables, left max and right max, and as we have discussed previously, initially left max is going to equal height at index 0 and right max will equal the last value in the height array which is given to us, and that would be height at index right because we have set right to equal the last index of the height array which is given to us. Now we will go over the height array which is given to us. We will just do one pass, and for that we will use a while loop, and we can say while left less than right. We'll keep looping, and once we come out of this while loop we will just return the answer. Now comes the tricky part. Inside this we'll have to decide which pointer to move. Okay, so let's write a comment over here, decide which pointer to move. Again, we have these two pointers, left and right, and the way that we are going to decide this is by checking if left max is less than or equal to right max. If this is the case, then we will decide to move the left pointer, and otherwise if that is not the case, then we will move the right pointer. Okay, now again this is helpful because if we move the left pointer, then we can be sure that left max is less than or equal to right max, and therefore we don't need to consider right max. We'll be able to compute the water that can be stored at that particular place at the index left. Okay, because we are moving the left pointer, we'll be able to compute the water that we can store at index left just using left max and the height at index left. Again, we have discussed that already. Now let's go ahead and implement that over here. Now let's say left max is less than or equal to right max. Now in this case, first we can increment the left pointer because we have to move the left pointer, and then we'll compute the new left max, which will be the maximum between what we already have at left max and the height at index left. Okay, now again we have also discussed why this is. We are always taking at a particular index the left max as the largest value to the left of that index and including the value at that particular index. Okay, so that's why we are saying left max is the max between these two, and we have discussed the logic for that previously. This will ensure that we never get a negative value for the amount of water that can be stored at a particular index. Now once we have the new left max, we can say that the water that can be stored at index left would be left max height at index left. Okay, so this will be the water that we can store, and then you just have to add this to the answer. Again, you could just write over here answer plus is equal to this value over here. Now notice we are not using right max over here, and the reason is that we are sure, again remember the way that we did this earlier was we found the minimum between left max and right max, and then we subtracted height at that particular index from this. But we don't need to do that over here because we already know that left max is less than or equal to right max. So that's why we don't need to check this any longer over here. Okay, we know that left max will be the lower value, or it can be at max equal to right max. So if that is the case, now because we know that, we can directly write over here left max minus height at left will be the water that can be stored at index left. Okay, now again let's proceed and complete this part. So if this is not the case, then we know that right max is less than left max. Okay, so in this case we will move the right pointer, and moving the right pointer means decreasing it by 1. Okay, and then we'll have to compute the new right max, which will be the maximum between what we already have at right max and the height at index right. Okay, which is where the right pointer is pointing to at this moment, and we are trying to find the water that we can store at index right. Again, let me write that over here. Our aim after moving, okay, after we move the right pointer, let's write it over here. Our aim is to calculate the water we can store at index right. Similarly over here it would be at index left. Let me paste this over here as well. Oops. Okay, so again that's what we did over here, right? So that's why we are just doing one pass. So when this fails, we would have completed one pass, we would have gone over all the indices, and we would have computed the water that can be stored given the array, the height array. Okay, so over here right max is the maximum between what we already have at right max and the height at index right, and then we can just say answer plus is equal to right max height at index right. Notice again, we don't need to check the minimum between right max and left max because we already know that right max will definitely be less than left max. Okay, so that's why we can directly write right max over here and we have our answer. And then finally we just need to return the answer once we come out of this while loop. So this is how we can solve this question using the 2-pointer approach. Now let's go ahead and run this and see if it's passing all the test cases. And you can see that yes, it's working, it's passing all the test cases. If you're trying to learn data structures and algorithms through a structured step-by-step approach, do check out my best-selling DSA with Python Udemy course. In this detailed hands-on course, you will dive deep into key data structures, powerful algorithmic techniques such as backtracking, dynamic programming, greedy strategies, crucial patterns such as sliding window, 2-pointers, merge intervals, and solve numerous Leetcode coding challenges to sharpen your problem-solving skills. Each concept is simplified with bite-sized animated lessons, relatable examples, and step-by-step coding demonstrations. By the end of this course, you will develop deep confidence to tackle DSA coding problems. To know more about this course, click on the link in the description and take your Python problem-solving skills to the next level.